All right, welcome everyone to our fourth lesson of Calculus 2. What we're going to be doing today is we're going to continue learning about how to integrate trig functions. Now, like I said last time, we already know how to integrate all 6 of the basic trig functions among a few others, like maybe secant squared or something. But if you have powers of trig functions that are multiplied together, those could be difficult to deal with. So last time we saw how to deal with products of powers of sine and cosine, and today we're going to learn how to deal with the other 4 trig functions: secant, tangent, cosecant, and cotangent. Now, just like we did with sine and cosine, we can break this up into cases based on what the power of secant and tangent is. We're going to do secant and tangent first, then cosecant, cotangent. So right now we're going to focus on integrals of this form. Secant, what did I use as the label for that? To the n, and tangent to the m. And depending on whether m and n are odd or even, it's going to change what we're going to end up doing here. Okay, so there's going to be 3 cases for this one. So case one is where n is even and m is even or odd. So effectively what this is saying is that it doesn't matter what m is at all. It could be any, well, I guess whole number. Yes, it still has to be a whole number. But secant just needs to have an even power. So what are we supposed to do in this case right here? Oh, is there some issue with the audio? Is that okay? Okay, looks like a good number of people can hear it. All right. So let's take a look here at an example that uses this case. Example 1. Let's do the integral of secant to the 4th times tangent cubed. All right. So last time with sines and cosines, what we did is we broke off a piece of the integral, put it at the end, and then used it as fodder for the u substitution. And that's exactly what we're going to be doing this time as well. Only this time, what I'm going to do is I'm going to move off 2 powers of secant to the end. So if I pull off 2 powers of secant here, I'm left with secant squared. I have tangent cubed. And then at the end, I have secant squared. All right, so what am I going to do with this now? Now, just like last time where we used the Pythagorean identity to convert between sines and cosines, today we're going to use the Pythagorean identity to convert between secants and tangents. Now remember, the identity for this, it's going to be relevant for us, is that tangent squared of x plus 1 is secant squared. Okay, so that's going to be our relevant identity for this class. Now what we're going to do here is, except for the secant squared that we pulled off at the end, we're going to turn all of the remaining secants into tangents. All right, so since secant squared is 1 plus tangent squared, that's exactly what I'm going to put here. All right. And then I bet you guys could guess what's going to come next. Actually, let me ask you guys, what do you think we're going to do next now? U substitution, that's right. Once all of the secants are gone, except for these, we're going to do a u sub, and our u will be none other than tangent. And then our motivation for doing this is revealed when we do the derivative of our u. We have secant squared of x dx, and thankfully we set that aside earlier in our integral right here. All right, so now we can safely put in our substitution. So we have u squared plus 1, and then we have u cubed here, and then secant squared of x dx is the du. All right, and just as before, we end up getting a nice polynomial integral, and we're back to Calc 1 mode here. So what I'm going to do is I'm going to distribute this, u to the 5th plus u cubed, and then I'm just going to do the power rule. So I have u to the 6th over 6, and then u to the 4th over 4, And then we have plus c. And then finally, as with all u substitutions, we need to return to our original variable here. And we just simply remember that u was tangent. So we end up getting tangent to the sixth divided by 6, plus tangent to the fourth divided by 4 plus c. And there we go. So there is our integral here. So the moral of the story is whenever we have an even power of secant, we move 2 of them off. And the reason why I needed to be even is if you subtract 2 from an even number, you still have an even number. If we still have an even number, we can use this right here. So this will work when n is even, and m could be any parity. It could be odd or even. Like this could have been tangent to the fourth. This problem would have went almost exactly the same way as it did with tangent cubed.
Professor, you don't even need tangent, do you? Because you can just break off secants and make them tangents, right? Like if you have like secant to the 8th, you can just break it up into secant squared times secant to the 6th.
Oh, yeah, that's right. So yeah, what you're saying is m can be 0. That's right. Yeah, so we could have done secant to the 8th in exactly the same way. Absolutely right. All right, so let's have you guys try that. Actually, it's kind of funny you mentioned that. Our practice problem is very similar to this. Our practice problem 1 is the integral of secant to the 6th. So it's a milder version of what you suggested. All right, so why don't you guys take a few minutes and try to use our new technique on the integral of secant to the 6th here. And don't forget to, at the end of class, put in all your answers into Canvas. Also, one thing I want to warn you guys about with Canvas, this happens to a fair number of people. If you're using Canvas on your laptop and you're scrolling with your arrow keys, make sure that you don't have the multiple choice section highlighted, because if you hit the arrow key on that, it'll actually move what your answer is. So be very careful if you're scrolling down a Canvas quiz page with your arrow keys. I've unfortunately had some bad experiences with that.
I have a quick question. With our tests for the exam, can we use like track mouses and separate keypads?
I mean, as long as you're just using one, I don't really see the issue with that. Yeah, I don't think that'll be a problem. We'll talk about that once we get closer to the exam.
Okay, thank you.
Kate, are you also drinking a lime bubbly?
No, I'm drinking like a sparkling apple thing.
Oh, okay.
But it looks very similar. I almost grabbed like a lime bubbly.
Okay, yeah, it had the light green color.
Yeah.
It's even. Do we have to do something different? Yeah, remember, it doesn't matter what the power of tangent is. You could still do this in exactly the same way. So just break off a secant squared and then change all of the other secants into tangents using the Pythagorean identity. Give you guys another minute or so here. This one's a little bit more work than the previous one. The hand. I think I killed that ant by mistake later on in the class when he was off screen. Sorry, guys. All right, anyways, let's console ourselves by doing the integral of secant to the sixth here. So as in the previous example up here, I'm going to break off a secant squared, put it at the end. So once I have this at the end, which is going to be useful for my u substitution, I need to change all of my remaining secants into tangents. So the way that's going to work here is we have to recognize that secant squared squared is secant to the fourth. And then secant squared, we scroll back up here, is going to turn into 1 plus tangent squared. All right. So now everything we have in this integral, except for the secant squared we saved, is tangents or constants. So that means we're ready to do our u substitution here. So we have u is tangent and du is secant squared. All right. So then once we put that substitution in here, we have 1 plus u squared squared, and then the rest of this will turn into a du. All right, oops, going a little too far down. All right, so if I FOIL this out, I have 1 plus 2u squared plus u to the fourth du, if I do the FOILing there. All right, and then once I do my power rule on each of these, I have u and 2/3 u cubed and u to the fifth over 5 right here. Then I'm almost done. All I need to do now is plug back in tangent for u. So I have tangent plus 2/3 tangent cubed plus tangent to the fifth over 5 plus c. There we go. There's going to be our antiderivative of secant to the sixth power. All right. All right, so that's some good practice. That was case one. Case two. So we talked about when n is even, the power of secant is even. Now let's move on to when the power of secant is odd. So n is odd. Remember, n was our power of secant. And m is also odd. So if both of the powers are odd, we can do this second case right here. All right, so let's take a look at an example of this. How are we going to do this? Let's say we have the integral of secant cubed times tangent cubed. Okay, now we're going to have the same philosophy for this example. We're still going to move something to the end, transform all of our other functions, and then do a u substitution. So that's still going to be how this is going to work, only the thing we're going to move to the end is different. This time, if both of these powers are odd, like in this example, I'm going to move one of each to the end. So I have secant squared, tangent squared, and then I have a secant of x, tangent of x dx. Now, can anyone maybe see why I chose to do that based on all of the other things we've done? What do you think I'm going to do in the future? Yeah, so someone in the audience says that's the derivative. It's not of secant squared, though, it's of secant. But that's right, yes. Yeah, so this is the derivative of secant, so we're going to do that as a u substitution a little bit later. So it's okay if these are secant squareds, that's totally fine. We do want this to turn into secants, so we could do that u substitution. All right, so remember, tangent squared of x plus 1 is secant squared. So we could simply subtract 1 and have the tangent squared is secant squared minus 1. All right, so let's turn everything except for this into tangents, or sorry, secants. All right. right? We still have this at the end. And then now we are ready to do our u substitution, since all of this stuff is a secant, and then this will be our du. So u will be secant of x, and du will be secant of x, tangent of x dx. All right, so let's see. We have a secant squared here. That will be u squared. And then we have a secant squared there. That will also be a u squared. And then we have this guy at the end, which its whole purpose was to be a du. All right. Let's go ahead and distribute this here. U to the fourth minus u squared du. And then we could just go ahead and do a nice power rule here. So we have u to the fifth over 5 minus u cubed over 3 plus c, once we do the power rule right there. And then finally, as always, our last step is to convert back into x's. So this will be secant to the fifth of x minus secant cubed of x over 3 plus c. And there we go. So there's going to be our derivative right here. Or sorry, our antiderivative. All right, so with that in mind, why don't you guys try another example? We kind of have back-to-back ones here, using this technique. So I'll give you one of the case 2 ones where they both have odd powers. Why don't we try secant to the fifth times tangent? So in pretty much exactly the same way that I just did this example, why don't you guys do this?
This one's so much easier than the other one.
Yeah. There's no foiling necessary.
Trig and algebra are harder than calculus. It's not even a joke.
Oftentimes the hard part about calculus is you doing the algebra and trig. A lot of times that stuff gets pretty messy. What's the basic idea for this case again? The thing we're moving to the end is a copy of secant and a copy of tangent. And that's going to end up being our du when we have u as secant. Yeah, unfortunately, we need to memorize both of those types of identities for this semester. So we'll definitely be using the half angle identities, and we'll be using one of the double angle identities.
If it's sine or cosine, that's not bad for double angles, but tangent is messy. And secant, cotangent, and cosecant are messy too.
Yeah, those are pretty bad. I mean, you could get all of those by using the sine and cosine ones, but
yeah, I mean, deriving is not hard. It's just tedious.
Yeah, and for all that effort, they're not very useful. I'll give you guys another minute or so. Yeah, this one doesn't take as long. Actually, it looks like most people are done. We can go ahead and do this one. We're definitely going to need a lot of time for the next one, though. The next one is not fun. All right. So with this one, we see this is definitely going to be a case 2 for secant and tangent because we have an odd power of secant and an odd power of tangent, which is 1. So I'm going to break off at least one of those and move them to the end. So effectively, all I'm doing is breaking off a secant from here and keeping the tangent at the end. However you do it, you just need to ensure that you have this at the end of your integral right here. All right. Now what we do is we turn all of the remaining functions into secants, but fortunately we don't need to do that step here. We just make u is secant, du is secant times tangent, and then we're ready to go. So this is going to be a u to the fourth This is going to be du. And this is another nice power rule one. This is u to the 5th over 5 plus c. And we could substitute in for our u and get secant to the 5th over 5 plus c. There we go. So that's how we do that one. These are going to be the only two practice problems today. So if you have both of those and you have the correct answer that we got for both of these, which the first one I believe was this, and then we have this one right here, then feel free to go ahead and submit it. All right. Now we're going to move on to case 3. And so we really only have one option left. We've done where the power of secant was even. We did where the power of secant was odd and the other one was odd. So now we just need to deal with when the power of secant is odd and when the power of tangent is even. That's the only case we have left. And that's case 3. So n is odd. That's the power of secant. M is even. Unfortunately, this case is significantly more difficult and tedious than the other ones. So let's see an example here. Let's see. Our example for this one, and the scary part is this is probably one of the easiest examples of this, but it's still going to take a while. It's secant cubed times tangent squared. Okay. So we're going to integrate this guy. Now, unlike the other ones, we're not going to be able to move anything to the end and have that be the du for a u substitution. Because let's say we moved, like, say, a secant squared to the end. Let's say we made this equal to secant tangent squared and then secant squared. So let's say we tried to treat it like case 1. We could make u be tangent, and that wouldn't be a problem for this, but it would be a problem here because the secant isn't squared. So we can't use the Pythagorean identity very easily. I mean, I guess we could have a square root of something in there, but that's not going to make the integral any easier. We can't do it this way. That's out. And if we try to do it in the way that we just did the problems, where we move a secant and a tangent to the end, we have secant squared times tangent, and then secant, and then tangent. And we have the same problem here, only it's with tangents. We don't have an even power of tangent, so we can't easily use the Pythagorean identity to convert this over. So neither of the previous methods are going to work. Maybe for a specific problem, there's some kind of bizarre power of secant or tangent that might work, but that will only work for very specific cases. So we really can't do this method at all in generality. So what we're going to do instead is we're going to turn everything into secants and do the problem that way. So here's where I started. And now I'm going to turn this tangent squared into secants. So tangent squared is secant squared minus 1. And then if I distribute my secants here, I have secant to the 5th minus secant cubed. All right. And then what I'm going to do now is I'm going to split these up into 2 different integrals because we're going to handle them separately. So from here, I'm going to write this as secant to the 5th of x dx minus the integral of secant cubed of x. Okay, so I'm going to forget about this one for now. We'll worry about this guy later. And I'm going to just do the integral of secant to the 5th. Okay, well, how am I going to do this? What I'm going to do is I'm going to do integration by parts. That's why this section came after IBP, because we need to use it for some of these problems. Now, what am I going to do here? So it looks like I just have a secant to the 5th. So you might think, oh, I'm just going to have u be secant to the 5th and dv be dx, but it's not going to quite work that way. I'm going to have u be secant cubed and dv be secant squared of x dx. Okay, now why did I split it up that way? Well, remember, whatever we put for our dv, we need to find the antiderivative, right? And the antiderivative of secant squared is going to be tangent. So at least we have a nice antiderivative here. Unfortunately, there's no way to get around this. We're going to have to do kind of a icky chain rule for this. So my outer function is cubed. So I'm going to do the derivative of something cubed. So I have 3, and then I have the inside squared now. And then I multiply by the derivative of secant, which is secant times tangent. Okay, so then when I combine all of this back together, I have 3 secant cubed of x tangent of x. Okay, so let's get a little bit more organized here. Let's rewrite what we have. Our original integral was the integral of secant cubed tangent squared. And based on this integration by parts here, we do u times v. So it's going to be secant cubed times tangent. And then we're going to subtract the integral of v, oh, this should be du, right here. So we subtract, and then this 3 is going to be a constant. I'm just going to move that out. And then what do we have? We have secant cubed tangent here, and then we multiply by another tangent. So all in all, that's going to end up giving us secant cubed tangent squared of x. And finally, we have this guy, which we haven't even messed with yet. All righty. So this is what we have so far. And unfortunately, it looks like we're just making this messier and messier. It doesn't look like we're getting closer. But what's one nice thing that we can maybe do here? Does anyone see anything convenient?
You can actually do the middle integral.
Well, so what we could
You
do
can add the
is we'll
3
involve the middle
over.
integral. We have -3 of it here, and we have 1 of it here. But what we could do is we could do that same trick that we did with integration by parts and add 3 copies of the integral to both sides. So I'm going to add 3 of the integral on the left. I'm going to add 3 of the integral on the right. And thankfully, these will cancel out. So we don't need to worry about that now. But on this side, we're going to have 4 of it. Okay, so let's look at the aftermath of this. We have the secant cubed tangent of x here, and then we subtract and have the integral of secant cubed. Okay, so what I'm going to do now is I'm going to kind of do some work on the side here. What I'm going to do is I'm going to try to figure out what the integral of secant cubed is. And then once I get that, I'm just going to stick it back in here. And then I'll have my final answer at that point. So what I'm going to do is I'm going to do the integral of secant cubed. Okay. Now the way I'm going to do this is I'm going to do this in the same way that I approached the integral of secant to the 5th. I know that if I make my dv be secant squared, I'm going to get a nice v out of that. So I'm going to make my u be secant and my dv be secant squared. So du will be the derivative of this, secant times tangent, and v will be the antiderivative of this, which is tangent. Okay, let's see what we get from that. So our original integral is going to be tangent times secant, and then we subtract the integral of secant times tangent squared. Okay, now remember the whole goal is to get this to be easier than before, but unfortunately this is still a case 3 integral. We have an odd power for secant and an even power for tangent. So at first it doesn't look like I did anything productive, but what I'm going to do is I'm going to turn this tangent into secants. And that will be our secret technique here that will help us. Oh, push it up, thank you. Yeah, so people in the chat seem to be confused by this. Don't worry, this is by far the trickiest one. So it's okay if you're confused at first. Okay, so let's see here. I was going to turn this into tangents. Tangent squared is secant squared minus 1. And then I'm going to distribute. And then I'm going to distribute the negative here and split up the integrals. So I have minus secant cubed of x, and then minus and minus will make plus secant of x. So notice what we've been doing for this whole problem. In the very beginning of the problem, we ended up with a secant to the fifth, right? So we did an integration by parts. We did our sly little trick where we added a copy of the integral to both sides, and then we needed to do an integral of secant cubed. Okay, so we do the integral of secant cubed, and we do integration by parts again. We do a little trick here, and then we end up with the integral of secant. So effectively what we're doing in this process is we're sort of chipping away at the powers of secant. Every time we do an integration by parts, we're effectively cutting off 2 powers of our secant. Now the nice thing here is that now we're just at the integral of secant. And the integral of secant is hopefully something they mentioned to you in Calculus 1. This is going to be the natural log of absolute value of secant plus tangent. Okay, so that one, we don't need to do any more IBP. We just have the answer for that one. All right. Okay, so remember, all of this was the integral of secant cubed. This is still kind of our side work here. So this is secant cubed, and then once again, I could do this trick where I add a copy of the integral to both sides. So I add this over here, and I have 2 of this integral now. All right, and then I'd simply divide by the 2. So I'm going to get rid of that and divide by a 2, and then have a plus c. All right, so we were able to figure out what the integral of secant cubed is. Now, usually I don't like to suggest that people memorize things in math. It's better to understand how something works so you can kind of just create the knowledge whenever you want rather than just trying in vain to memorize everything. This is an exception though. I would memorize this integral. The integral of secant cubed is 1/2 secant tangent, and then we have ln of secant plus tangent right here. Now, this may look kind of like a lot to memorize here. There's actually an easy way to memorize this. This is 1/2 the derivative of secant plus the integral of secant, meaning it's the average of the 2. If you add 2 things together, divide by 2, that's the average. So it's the average of the derivative and the secant here. Where did the natural log come from? This natural log part is just the integral of secant of x. The integral of secant is this natural log right here. Okay, so anyways, we now know that the integral of secant is this average of the derivative and integral. That means we can go all the way back up here and finish our other problem. So we have 4 times this integral. Okay, and we have this extra piece that we got from the IBP earlier. And then now this time we actually know what the integral of secant cubed is. It's 1/2 secant tangent plus this natural log. There we go. So effectively we're taking this and we're putting it in right there. And now finally, all I have to do to finish this off is I'm going to divide by 4. So our final answer here, our original integral, is going to be secant cubed tangent of x over 4, and then minus 1/8, because we already had a half there, so it's going to be minus 1/8, secant of x tangent of x plus natural log of absolute value of secant plus tangent. And plus c, icing on the cake right there. There we go. So this was case 3. And obviously, I think it's pretty clear case 3 is significantly different from case 1 and case 2. Now, in the future, you don't need to do any of this work right here. in the future, don't worry about doing any of that. Just follow my suggestion and just memorize that the integral of secant cubed is that right there. Then you don't have to do any of this ever again. You don't need to rederive what this is. You could just use the result. And then we could have ended the problem back here instead. So that's kind of a shortcut, and I strongly encourage you to memorize that right here. And then we can go on. So effectively what we do in this process is we convert everything to secants, and then every time we go through an integration by parts, we cut the power of secant by 2. So whatever power we start at, whether it be 5, 7, 9, whatever, we need to do integration by parts until we get down to secant cubed. And then once we get to secant cubed, we could stick in this as our answer there. What happened when you divided by 4 to get the answer? So I had 4 of this integral, and I had these 2 pieces. So if I divide by 4, I have this over 4. But since I already had a coefficient of 1/2, I divide that by 4 to get -1/8. All right. Yeah, this one's definitely pretty long here. Yeah, so these ones are long no matter what. And notice that in this problem, these are relatively low powers of secant and tangent, meaning it definitely could be worse, unfortunately. So case three is frowny face. We don't really like this one very much. All right. So can I say that last part again? I'm not sure which part you meant.
You were describing taking the 4 from one side and then turning it into the 1/8.
Yeah, oh yeah, so I simply just divided both sides of this by 4. So this didn't have a coefficient, so now it's over 4. And then I have 1/2 of something. If I divide a half by 4, I get 1/8 right there.
Gotcha, thank you.
All right, wonderful. So this was our case 3 example. Now let's see, how much time do we have left in class here? Time is it? We have about 12 minutes, so it's a decent amount of time. So you may be wondering, okay, well, this was secant and tangent. We still have a third of the trig functions to go. We have cosecant and cotangent. How are those going to end up working here? And the nice answer is that, sorry, I don't think we're gonna have an early day today. So the nice thing about cosecant and cotangent, the cases are exactly the same as with secant and tangent. So cosecant's going to take the place of secant, and cotangent's going to take the place of tangent. And we could use all of the same 3 cases with those rules about the powers being odd or even to integrate things involving cosecant and cotangent. Yeah, that's the one thing that will be different. So someone in the audience asked, will there be negatives with this? And the answer is yes, because remember, the derivatives of these have negatives in them. So the derivative of cotangent is negative cosecant squared, and the derivative of cosecant of x is negative cosecant cotangent.
What's the integral of the cosecant to the third? Is it like similar to the secant to the third?
That's right, yeah. So the integral of cosecant to the third is going to be negative 1/2, and then we're going to have negative cosecant cotangent. Let's see, minus, oh, now I might get mixed up by a negative sign. Let's see. Natural log of absolute value of cosecant plus cotangent. Uh-oh. Might need to go through the whole thing again. It's very similar though. In general, when you do a derivative or integral of a co thing, the formula is identical to the non-co version. You just change everything to be co, and then you put a negative sign on it. So actually, in light of that, I think these should be plus here. All right, this is going to have a question mark though. We could figure it out though. We could figure it out by using integration by parts. We literally do exactly the same thing. So let's figure it out.
Yeah, it's a negative, positive, negative.
Okay, all right, so it's negative and then positive.
Yeah, so it's like negative cosecant x cotangent x plus ln in parentheses cosecant x minus cotangent x, not all over 2.
Oh, so the minus is in here, and then this is a plus. There's actually another form. This can be written in another way too. Well, here, look, for entertainment, if you guys want, you could go ahead and do integration by parts here to get a. I think it'll end up being maybe a different form of this. Whatever. That's not really the point of this. Although, yeah, it is going to be. Yeah, knowing cosecant cubed might be a good idea. What I'm going to do here is I'm just going to do a basic example of a cosecant cotangent integral, and it's not going to be a case 3 one. I don't want to go through all that again. So we have cosecant to the 4th times cotangent squared. Okay, so let's go ahead and try this one. If we have time at the end, we'll take a look at this. So what do you guys think I should do with this one? I have an even power of cosecant and an even power of cotangent. So what do you guys think I should do for this? Yeah, so yeah, the audience suggested we're going to pull off cosecants, and that's absolutely right. So we're going to pull off cosecant squared, and that's going to go to the end. So this is effectively case 1. Remember, case 1 is where our power of secant was even, so naturally it's going to work the same way if the power of cosecant is even. All right. Now what we're going to do is we're going to turn everything into cotangents. So here's the Pythagorean identity for cosecant and cotangent. Cosecant squared is cotangent squared plus 1. So we're going to substitute this in here. All right. And then what do you think is going to happen next here? We're going to end up doing u is cotangent of x. Now this is where the negatives will begin kind of seeping in to the problem here, because the derivative of cotangent is negative cosecant squared. All right, now we don't have an extra negative lying around in the problem here, so I'm going to move the negative over to the du side. Okay, so now I'm ready to convert my integral into u's. So I have that negative I just got from the du. I'm going to have u squared plus 1, and then I'm going to have u squared here, and then we're going to have du for that. All right, so I'm going to distribute here. We have u to the 4th plus u squared. All right, and then we're just going to go ahead and do a power rule. So I have negative u to the 5th over 5 minus u cubed over 3 plus c. And then finally, we go back to cotangents. So this is cotangent to the 5th over 5 minus cotangent cubed over 3. And then that's going to be plus c right here. All right, so there we go. So the good news about cosecant and cotangent is you effectively get those free if you know the secant and tangent versions of them as well. All right. Now, as evidenced by my inability to remember what this is, cosecants and cotangents are by far less common than the other trig functions. I mean, I'm sure you guys have already kind of experienced this yourselves, but even if you look at applied fields and things like that, sine, cosine, secant, tangent, those see pretty common use, but cosecant and cotangent, maybe not so much. So integrals like this are pretty uncommon in practice, but it's still good to kind of at least have some experience doing them here. All right, let's see. How are we doing on our time here? All right, we got 5 minutes. I'm going to go ahead and do this. I'm going to go ahead and do this from scratch. All right, so it's good practice of integration by parts and doing a trig integral. So we have the integral of cosecant cubed dx. All right, and then I was going to do u is cosecant and dv is cosecant squared. Okay. Now the derivative of u is going to be negative cosecant cotangent. And the antiderivative of cosecant squared right here is going to be negative cotangent of x. All right. So let's write what we have here now. All right, so we have u times v, so it's going to be negative cosecant of x times cotangent of x. All right, and then I subtract the integral of these guys right here. Now, because we already have two negatives in here, those will cancel out, and I'm going to get cosecant times cotangent squared. All righty. So now what I'm going to do is cotangent squared right here is going to turn into cosecants. Okay. So cotangent squared is going to be cosecant squared minus 1. All righty. So if I distribute this and split up the integrals, all right, I have a negative and a negative, so that's going to be a positive here. Oops, forgot that. All right, so then I have negative this integral right here, and then I can add that over to this side. Okay, so then I have negative cosecant of x, cotangent of x, and then I'm going to have the integral of cosecant of x right there. All right, and then the final thing we need to do here is just divide by 2, and then we're finished. So actually, this is the derivative of cosecant of x, and this is the integral of cosecant of x as well. So you can memorize this one in exactly the same way that you memorized the secant cubed one. So that's what's going to happen here. So kind of like the secant cubed one, this is going to be 1/2 the derivative of cosecant plus the integral cosecant. All right. So there we go. Yeah, so you can memorize those in the same way. They work exactly the same way. Yeah, what's up? Let's see. So this is going to be negative the natural log of cosecant plus cotangent, if I'm not mistaken here. There's more than one form of that, though. It always trips me up. But yeah, okay, that's what that's going to be. All right, I think we're done here for now. So this is all we're going to do with trig integrals. And next time, we're going to learn how to turn other types of integrals into trig integrals. So now that we know how to do these trig integrals, and some of them are pretty tricky, but we won't see case 3 very often, thankfully. But now that we know how to do these trig integrals, we can turn other integrals into them and figure out how to do those. So that will be what we're going to be learning about on Monday. So I will go ahead and see you guys then.
Thank you.
Thank you.
Thank you.
Thank you.
Gracias.
Thank you.